And we're supposed to find the equation of the plane through these points 0, 6, 6, 6, 0, 6, and 6, 6, 0. Okay, so last time we discussed a little bit how this works. So this is the vector equation of the plane, the scalar equation of the plane. And the idea is if you have a normal vector and you have a point on the plane, then you can use that to get the equation for the plane. Okay, so the normal vector is where these A, B, and C comes in. And then the point is where the x0, y0, z0 comes in. Okay, so for number 7, we have 3 points, but no normal. Boo. So what you can do, so I guess the proper way to proceed here would be, let's call this P, that Q, and that R. Okay? And then what we're going to do is we're going to use these points to, so like, the idea is this. If this is P, Q, and R, oh, someone mute the...
Ma, come outside, there's a fucking moose!
Here, your mic is on.
Where the fuck are you going?
Ma!
Ma!
Yeah, I'll just mute him. Okay, so it's just, if he wants to come back, then just let me know. Okay, so anyways, the idea is, that you have these 3 points right here. And if you form these vectors, these 2 vectors, and then you take the cross product of those 2 vectors, you'll get a vector that's normal to these 2 vectors. But that means it's going to be normal to the plane, right? Okay, so our normal vector is going to be the cross product of PQ and PR. And that is going to be normal to the plane. Okay, so PQ is, I guess I can do it right here. That's going to be this minus this. So what do we get? We get 6, -6, and 0. I like zeros when we're doing this. This is fun to get zeros. And then PR is going to be this minus this, so that's 6, 0, and -6. Okay, so the cross product is going to be, you have these, you have 36i, and then 0j and 0k, minus, that's a -36k, and then 0i, and also a -36j. Oh, that's interesting. So we have 36i plus 36j plus 36k. Now they're all 36s, so we can actually, if you want, you can just use the vector 1, 1, 1. Okay, so you can just divide everything by 36 and use that vector instead. We just need a vector that's normal. It doesn't have to be any, it doesn't have to be a specified vector, just any vector that's normal. And this is the easiest one, 1, 1, 1. Instead of using 36, 36, 36. And so that's our ABC. And then you just go, you just like choose one of these points. They probably want us to choose the first one. So let's just choose the first one. So I'm using that right there. And the equation is going to be, just plug the numbers in here, just plug 1s in for A, B, and C, and then 0, 6, and 6, and for x0, y0, and z0. So that gives us x minus 0 plus 1 times y minus 6 plus 1 times z minus 6. Okay, so those 6's are going there, equals 0. Okay, so once again, what this represents is if you have another point, so let's say these are in a plane. The normal vector is going to be like that. And if you have any other point in the plane x, y, z that's in the plane where that's where p, q, and r live, then this vector here to that point x, y, z is going to be normal with this. It should be normal with the normal vector. It will be in the plane if only if it's if only if these two vectors are normal, or if you're at the point p0 or orthogonal, not normal, orthogonal. I guess normal is the same as normal, I guess. Okay. So we have 2 minus 6's, so we just get x plus y plus z equals 12. So combine those and take it to the other side, and I think that will do it. Let's see. See if it accepts that answer.
You got it right.
Yay. Accepted it. Yay. Okay.
So brother,
number,
to get the vector of n, it's just 1, 1, 1. Did you just divide everything by 1 because it's all 36's?
yeah, I divide everything by 36.
Okay. All right. Sounds good.
It just makes things easier. Okay, number 8. Let's see. Use intercepts to sketch the plane 5x plus y plus 3z equals 15. And so what you're going to do here, this is just a multiple choice. So we have the z-axis there, the y-axis, and then we have the x-axis coming out this way. And when it says intercepts, then it works this way. To get the x-intercept, or say the point that's along the x-axis, right here, where the plane is the plane's actually gonna cut through there, there, and there. But to find where it does, then the x-intercept is the point where it cuts the x-axis. And to get that, you set y and z both equal to 0. And then, so that's 0, 0. Those are 0, and so you get 5x equals 15, which means that x is 3. That means it's going to cut through right here at 3. Okay, and then what's the y-intercept going to be?
You let x and z go to 0.
Yeah, and so yeah, that gives you y equals
15.
Yes, 15. Okay, so the y is going to be out here at 15. And then the z-intercept, what's the z-intercept going to be?
Is it 5?
Yes, that's going to be 5. Okay, so you set both those equal to 0, you get 3z equals 15, divided by 3, you get 5. Okay, so 5. Okay, and so then the plane is going to cut through, the plane's going to cut through those 3 points and going to go on forever in all these directions. So, which graph does it look like?
Top left.
Yes, it's the top left. Okay, moving along. Number 9. Find the point at which the line intersects the plane. So we have this plane here, here's the equation of a plane. So notice this is kind of in the form of the other planes that we're talking about. So like there's a plane right there, and that's a plane. Okay, so that's in that form. And then here's a line. This is the parametric form of the equation of a line. Okay, and so they want to know where this line intersects the plane. So it's going to be a line, and then there's a plane, and they could intersect each other. Probably gonna, that's usually the case, but sometimes planes don't intersect lines. So I'll let you guys think, what do you think we should do with this? How do you think we should find where the line intersects the plane? So here's the line, here's the plane. Can
you plug those equations into the big equation?
Exactly. So here, so here's the equation of the plane, right? You have that, right? So this can go in to there, and that's going to give you 2 minus t, 2t. And then the y goes in to there, and then the z goes into there, and you get that. So we have this big equation here. So let's see, 2 minus 2t plus 6t minus 1 minus t equals 4. And let's see, combining all the t's, you get, it looks like 5t. And then you have 2.
Oh, yeah, your mic is on again.
Minus 1. And that's going to be 3, I think. Yeah, so 2 minus 1 is 1. To take it to the other side, and subtract to 3. Oh, dang, this is not a very nice number. 3/5. Aw. Okay, so t is equal to 3/5 unless I made some mistake somewhere. Oh, this is not very nice. Okay, so now what do you think we do? So we found 3/5, t equal to 3/5. Now we want to find the point. And so when it says point, it's going to be like this, right? Something, comma, something, comma, something. It's going to be of that form. So this is not going to work as an answer. Oh, plus you can't even put it in.
Then can you plug them back into the original equations and solve for x?
Yes. Yes, yes. Now you plug it into there. Okay. So now you're going to take this and plug it in to here. So x equals 2 minus 2 times 3/5, which is 2 minus 6/5, which is 4/5. Then y is 3 times 3/5, which is 9/5. And then z is 1 plus 3/5, which is 8/5. Okay, so we're going to put in 4/5, 9/5, and 8/5, and let's see if that works. Okay, so 4/5, 9/5, and 8/5. And something's wrong. It didn't accept it. How dare they not accept my answer? I worked so hard for that answer. Okay, so something went wrong somehow.
Wait, did we plug those back into the big equation after we found the x and y's?
Into what equation? Oh, into here?
Yeah.
That would be good to check, I guess.
I mean, would that work?
They should work. So if we plug them into there, it should work. But it looks like they don't work because they didn't give me they said the answer was wrong. So if I plug it into the left-hand side, I get 4/5.
Hey, Brother Hirsch.
Yeah?
T should be equal to 1.
Oh yeah. Oh man, all that work for that. Okay, so here's the problem. So all that's wrong. Boo. And my arithmetic went bad.
Yeah, 3t equals 3.
Okay, so boo. Okay, so t is 1. That makes things a lot easier. Okay, so now x is going to be 0, y is going to be 3, and z is going to be 2. So I erase that. That, and that, and that, and that. And so 0, 3, and 2. Let's try that. Okay, so I take back what I said, and Webassign was correct in punishing me for making such a silly mistake with my arithmetic. Okay, so find direction numbers for the line of intersection of the points of the planes. Okay, so the idea here is you have two planes, and when you have two planes and they intersect, what does the intersection look like? Anybody? And what is the intersection? The intersection is a, you guys want to play hangman again? It's a 4-letter word. Okay, so the intersection of two lines is?
A point.
No, point is 5 letters. The intersection of two planes.
Is it a skew?
Line.
Yeah, it's a line. Okay. Okay, the intersection of two points, two planes
Great job,
is
Taylor.
a line.
Gracias.
Okay. So it's a line. Okay, and so when you say direction numbers, that's kind of a weird thing to say, direction numbers. Ooh. But I think that's a code for the direction vector of the plane, or the line, I mean. The direction vector of the line. Okay, so, dang, I'm not really good at drawing, but I would like to draw, let's say, here's my first plane right here. And then if I have another plane, maybe they intersect right there. Like that. So if I have two planes, they intersect right here. I want to know what I'm looking for is this vector here, or it could be that vector there, either one. So the one that goes in the direction of the line of intersection. Okay, that's what I'm looking for. And so, does anybody have an idea how to find that? I'll give you a few seconds, but I'd be surprised if anybody came up with this. Okay, so what you do is for this red plane, it's going to have a normal vector. Okay, and then the blue plane is also going to have a normal vector. And do you know that the normal vector for the red plane, what is let's say the red plane is this one here. What's the normal vector for this plane?
1, 1, 1.
Yes, it's 1, 1, 1. And then if this is the blue plane, the normal vector is 1, 0, 1. Okay, so it's just from the coefficients in the equation. Okay, as long as all of the x, y's, and z's are on the left-hand side of the equation. Okay, so if you take the cross product, of these two normal vectors, and I guess I should have written it right here instead. So maybe I erase that. Erase these, and maybe it'll see a little bit better if I do it right here. Let me do it right here on that. So this vector here on this plane in the red plane, it's normal to the plane, which means, and then this line is in the red plane. The line is in the red plane. So this red vector is normal to the direction vector of the line. And then likewise, the blue plane, the normal to the blue plane is also normal to the line. Okay, so these two vectors here are both normal to the direction of the line. So that means that to find the direction numbers or the direction vector of the line, we simply do what?
Cross product.
Yeah, you just take the cross product of those two, and that's going to give it to you. So lots of cross products in this section. I guess that's why they call it the cross product. Okay, so I1, 1, J, 1, 0. Okay, so taking the cross product, we have I plus J plus 0K, a minus, and then we have K, and 0, and then plus J. So that's going to be I, and the J's cancel. So I minus K, and that's going to be 1, 0, negative 1. Okay, so let's plug that in and see if Webassign agrees with our answer. Good for nothing.
You have to use vectors.
Let's see here. It didn't accept the vector form.
That didn't work.
Dang. Okay, so let's see here. What went wrong here?
Brother Hirsch, you don't need, just plug them in without parentheses or anything and it works.
Really? Seriously? Okay, so, okay, thanks for figuring that out. Okay, so, yeah, so you don't need that. So it's just 1, 0, -1. That's the answer. No parentheses or nothing. So I guess the direction numbers is code for, that's just direction numbers, 1, 0, -1. It's not like writing it as a vector or anything. Okay, that's weird. Okay, so just write the numbers like that and you're good. Okay, so number 11, find parametric equations for the line of intersection of the planes of these two planes. So now we want to find, it's kind of taking it a step further, and we want the parametric equations. And then part B is to find the angle between the planes. So, so this starts out really similar to the other one, because the first thing we want to do is take the cross product and find the direction vector of the plane. Okay, of the line. I'm sorry. So you're gonna take the cross product of these two. Okay, so this is 1, 1, 1. That's 1, 6, 6, and those are there. Okay, so that's gonna give me 6i plus j, and then plus 6k, and then subtract k and 6i and 6j. Okay, so the i's are gonna the 6 i's are gonna cancel out, and then you've got j minus 6j. That's gonna be -5j. And then you have 6k minus k, so that's 5k. And we're only interested in the direction, so let's divide by 5. Divide by 5, so we have 0, -1, 1. Okay, so that's the direction vector. And then what you need to do is, so this is the direction vector. And so that would be kind of like our, let me go back to the equation here. That would be like, so we're interested in the parametric equations. So for the line, so that would be this right here. And the vector that we just found is the ABC vector, okay, ABC. And so now we need to find a point though. Okay, so that's the direction vector. And when we write the equations down, it's going to be x0 plus a t. Let me. Okay, it's going to be x0 plus at, and then y0 plus bt, and then z0 plus ct. Okay, and the a is going to be 0, and the b is going to be -1, and the c is going to be 1. Okay, so the x0, y0 is z0, that's we need a point. So we need a point that's need 1 point. Now, these intersect in a line, right? These intersect in a line. So there's going to be lots and lots of points, but we just need 1. And so what we could do is we could set these both up as a system of equations and solve it, and then just pick one solution off. Okay, or sometimes what you can do is you can just like play around with and set some numbers equal to 0 and can just kind of see a solution. And then if you do that, then that's a lot easier. And so I see, I'm looking at this and I see a solution almost immediately. I see a solution almost immediately. If I set y and z both equal to 0, then if I set x equal to 6, that works, right? That's going to satisfy both equations. So 6, 0, 0 works. And so I'm going to just plug in a 6 here, and that's 0, so it's just going to be 6. And then this is going to be, that's going to be 0, so we just have negative t. So b becomes -1, and then that's going to be 0, so then I have t. Okay, so let's try that. 6, negative t, and t. 6, negative t, t. Okay, and then the last one, let me see. Okay, good, that said that's right. Okay, so then the second part, finding the angle between the planes. So remember from the previous section on dot products that this is the angle between planes. So in this case, what happens is you have one plane right here, and then you have the other plane like this. And then they intersect in this line, right? They intersect in this line. And you want to find what this angle is right here, the angle between the planes. So we'll say that's theta. Well, it turns out that if you take the normal to this line, and then the normal to the normal to the red plane, and then take the normal to the blue plane, that the angle between those normals is also going to be the same. Okay, because basically you're just shifting both of these vectors by, so we have this vector pointing this direction and that pointing that direction. If we added 90 degrees or added power over 2 to both of these vectors, then the angle is still going to be the same. So this angle, the angle between the normals is the same as the angle between the planes. Okay, so that means that we're just going to take the dot product of the two vectors, and that will be the numerator. And maybe it would help for me to write those down. So the normal to the first plane is 1, 1, 1. And the normal of the second plane is 1, 6, 6. And we need all these things right here. So n1 dot n2, that's going to be 1 plus 6 plus 6, which is 13. Wow. And then the length of the first vector is going to be the square root of 1, 1, 1, so square root of 3. And the length of the second vector, I should put arrows above these, is going to be the square root of 1 plus 36 plus 36. So I'm squaring those two and adding together. And so the cosine of theta is going to be 13 divided by the square root of 3 times, and then what's this, 73. So the angle is going to be the inverse cosine of 13 over the square root of 3 times 73. And they want it in degrees, so make sure your calculator is in degrees mode. And we'll go ahead and calculate the inverse cosine. And I get approximately 28.54. Or rather, 28.5. Okay, so 28.5 degrees. And that worked for me in Webassign. Okay, so great. Let's go to the next to number 12, which is the last problem. And they want us to find the distance between the given parallel planes. Okay, so here they have two planes that are parallel to each other. So let me just kind of try to give you a drawing of that situation. So there's one plane, and then you have another plane that is parallel to that plane. Something like that. And so you want to know, so you have a point up here in this plane, and a corresponding another point which could be the projection of that in this other plane. And you want to know what this distance is. Okay, so we want to know what's this distance right here between the two planes. Okay. So there's the formula for that right there. But let me try to give you an idea of how this works. Okay, so this is a specific case of a say a more general kind of problem, which is, let's say that you have, okay, let's say that we have let's say that we have a plane right here. Okay, well, okay, so we're going to ignore this problem for a minute and look at a different problem and kind of just give you some rationale for how that works. Okay, so if you have, that we have a plane here, let's say that we have a point up here. Okay, so we have a point. And we want to know what is the distance between the point and the plane. Okay, what's the distance between this point and the plane? Okay, and we'll call this point, we'll call it P1. And so it's up here above the plane. It could be below the plane. Let's think of it as above the plane. Okay, so here's how we can proceed. We come down here to the plane, to any point in the plane. Now, of course, if this point right here is not directly below the P1 point, then the distance between these 2 points is not going to be the distance between the point and the plane. Okay, because the shortest distance is where you come down. The shortest distance from the point to the plane would be where you come down directly like this, right? Okay, so, but the idea is you're going to choose any point in the plane, And then you're going to consider this vector here, right there. And we're going to look at this vector right there. And you also know the vector here. You know the vector. You don't know what this point is, but you know that this vector is the normal vector to the plane. And so you have another vector here formed by any point in the plane and the point up here. This vector, we'll call that B. And the scalar projection of the normal vector onto B, no, the scalar projection of B onto the normal vector is actually going to be the distance. Is actually going to be the distance. Okay, so if you project this vector B onto this normal vector, then that's going to be the distance. That's going to be the distance right here. So that's why the distance is the scalar projection of the of B onto N. Hey, do you guys kind of see that? The projection of B onto N would just be this. Okay, so N doesn't, maybe I've drawn this wrong. N doesn't necessarily have to be that long. Maybe N just comes to there, or maybe N goes all the way to there. Okay, maybe N is longer, maybe it's shorter. It's probably not going to just like come and reach this point. But the scalar projection onto N is going to be equal to that distance. Okay, so what this requires is that the normal to the plane be A, B, C, and that's why the A, the B, and the C get plugged into, and then the B vector would be this x1, x2, x3. I'm sorry, B vector would be x1, y1, z1, like that. Okay, so let's get down to work, kind of go through the problem. So basically what we need is a point that's in one of these planes. And we need points in each plane. We need a point from here and a point from there, basically, is what we need. Any points. And we already know that the normal vector is here, it's 3, 4, 1, right? We already know it's 3, 4, 1. 3, negative 4, 1, I'm sorry. We already know that. 3, negative 4, 1. And if we come here, then it's 6, negative 8, 2, which is a multiple of this. So just use this one as the normal vector. Okay, so now we need a point from, we'll take a point from here. We'll get a P0 from there, and we'll get a P1 from here. Okay, so what we just need to choose any point from there. So, wow. We'll just choose the easiest one possible. So if you go 0, if you set x and y both equal to 0, then z has to be 1/2, right? To work. Okay, now we'll just choose any point from the first one. And if you set x and y both equal to 0, then z has to be 12 for that to work. Okay, so this point from this plane, and that points from that plane. So now it means that your B vector is going to be P1 minus P0. So that's going to be 12 minus a half. So that's going to be 23. Wait. It's going to be 0, 0, 23 over 2. And so the scalar projection, so this distance is going to be, you can use this formula here. Okay, so let's see what's n dot b. So the normal right here, dot product with this is going to be 23 over 2. And then the length of n would be the square root of 9 plus 16 plus 1. So that's 23 over 2 over the square root of 26. Okay, 23 over 2 root 26. Okay, let's see if that works. Yay, it worked. Okay, so that's the answer right there.